So this video is about lipid metabolism, and whenever you eat a food that's got some fat in it, you obviously have to digest the lipid, digest the fat before you can metabolize it. So you put it in your mouth, no lipid digestion occurs in the mouth, nothing happens. And then when it gets into the stomach, through the churning of the stomach, there's this physical digestion a little bit, and you create this blob called chyme that sort of sits on top of all the gastric juices. And that's why sometimes when you eat a high fat meal and it's right on top and you get some acid reflux, they always tell you that high fat foods cause a lot of indigestion. And anyway, so it's because it's sitting right on top there. And while it's sitting there, you have these enzymes, these gastric lipase enzymes that begin to hydrolyze some of the ester bonds of the triglycerides. Now, your dietary fat is in the form of triacylglycerols or triglycerides. So that's what we're focusing on, those triacylglycerols. So the gastric lipases are breaking some of the ester bonds that connect the fatty acids to glycerol. Not a lot, only 10% is being done in the stomach. Okay, so I've got that over here with the enzyme gastric lipase. And then it goes into the small intestine. Now, this is one big blob, remember, of this chyme. It's going into the small intestine, and it needs to be emulsified because it's the only way you can get all of those bonds that need to be hydrolyzed. You've got the enzymes have to be able to get to all of the triacylglycerols. So who's the emulsifying agent? Bile. Remember, bile was an oxidation product of cholesterol. It is synthesized by the liver, stored in the gallbladder, and when you eat food that's got some fat in it, the bile is then sent into the small intestine to do emulsification. If you remember from an earlier video, whenever we're emulsifying something, you're allowing things that are non-polar to become droplets. So the oily fat is becoming droplets within the liquid of the small intestine, the water of the small intestine. So the bile will do that emulsification. And then you've got the pancreatic lipase enzymes come in and they begin to do the hydrolysis. Now, you don't do complete hydrolysis of the triacylglycerol. Normally, the triacylglycerol you hydrolyze two of the ester bonds. So you've got two fatty acids, and then what's left is a monoacylglycerol or a monoglyceride. So we have that over here. The small intestine bile kicks in, and then the pancreatic lipase is going to turn your triacylglycerol, TAG, into a monoacylglycerol plus two fatty acids. Okay, so hopefully you understand what these acronyms are. All right, and then what happens, it goes through the small intestine villi into the lymph. And the reason it doesn't go directly into the blood is that these lipids are very non-polar. So the lymph can handle them. So they go through the lymph. And then in order for these lipids to be carried in the blood, they have to be packaged with proteins. Proteins have polar ends and non-polar ends, and these lipoproteins carry the lipids to where they need to go, whether it's the adipose tissue, which is the fat tissue, and the adipocytes, which are the fat cells of the fat tissue, or to the liver or whatever. Those initial dietary lipids are packaged in these lipoproteins called chylomicrons. Here it is. And they are transported in the blood. All right? Then what? Well, it can be stored in the fat cells. So you can store, they become triglycerides again, and you can store them in the fat cells. And the fat cells are called, like I said, adipocytes. But what if you start to move? And what if you start to need all this lipids that you've stored in your fat cells and you want to get energy out of it? So this is what we're going to focus on next. Since we're done with digestion, we're ready to talk about metabolism or catabolism of the lipids. All right, so a lipase will turn your triacylglycerol into a glycerol, and 3 fatty acids. So lipase will break those 3 ester bonds. And now we need to do metabolism of glycerol and metabolism of the fatty acid. How are we going to get energy out of glycerol? How are we going to get energy out of the fatty acids? Okay, so glycerol goes through 2 steps. Glycerol, first step, becomes glycerol 3-phosphate. Okay, glycerol 3-phosphate then gets turned into dihydroxyacetone phosphate. You guys remember this one? Dihydroxyacetone phosphate was an intermediate in glycolysis, in carbohydrate catabolism. So how do we get energy out of glycerol? 2-step process. This is the second step. We turn glycerol ultimately into dihydroxyacetone phosphate. And then what happens to this? This goes into the glycolysis. It gets, remember, triose phosphate isomerase turns it into glyceraldehyde 3-phosphate, and then glyceraldehyde 3-phosphate goes into that step 6 with glyceraldehyde 3-phosphate dehydrogenase, and eventually glycerol ends up as pyruvate, okay? And then pyruvate gets turned into acetyl-CoA, et cetera, et cetera. So we can get energy out of glycerol. Well, how do we get energy out of the fatty acids? This, by the way, all of this is in the cytoplasm. So these steps are in the cytoplasm. Remember, all of glycolysis is in the cytoplasm also. Now, what happens with the fatty acids? The fatty acids have to get activated, and then they have to get transported into the mitochondria, because how we're going to chop them up and turn them into acetyl-CoA is all occurring in the mitochondria. So let's focus on that. It's a several-step process. So let's say we have this fatty acid. Could be any fatty acid. Let's say we have this 18-carbon fatty acid, and it's saturated. You guys remember its name? An 18-carbon fatty acid that is saturated is stearic acid. Good. I hope you remember. So let's say I've got stearic acid and I want to get energy out of it. Remember, if this was a triglyceride, if it was a simple triglyceride, you have 3 stearic acids. If it was mixed, it could be a stearic, an oleic, a palmitic. But let's say we've got 1 fatty acid right now. It's stearic acid. And this is in the cytoplasm. And what you have to do is you have to first activate it. And you activate it using an ATP. But here's something different happens. When you take this fatty acid and you activate it with ATP, and then we're throwing in a coenzyme A, you end up breaking 2 high energy bonds of that ATP. So instead of becoming ADP, an inorganic phosphate, it becomes AMP and 2 inorganic phosphates. Okay, so you're breaking 2 high energy bonds. So what we do in biochemistry is that if you're breaking 2 high energy bonds of ATP, it's as if you're using 2 ATPs. So in order to start getting energy out of a fatty acid, you need to first put 2 ATPs in order to get the process started. Okay, sort of like what we did with glycolysis, if you remember. We put an ATP into the hexokinase reaction, and we put another ATP into the phosphofructokinase reaction, if you remember the carbohydrate metabolism chapter. Anyway, 2 ATPs are being used, the equivalent of 2 ATPs are being used, and then you end up having this acyl-CoA being formed. Sometimes in the book they have CoAsh because you have this sulfahedral group, and a sulfur is hooking up to the acyl. The term acyl just means fatty acid. Okay? All right, so we first activated it. The second step, we have to transport it from the cytoplasm into the mitochondria. And that transport into the mitochondria is via a molecule called carnitine. So just put that in your notes. Carnitine transports the acyl group into the mitochondria. Okay, and once it transports it into the mitochondria, it sticks it back onto a coenzyme A. So right now, we're in the mitochondria, and we have an acyl-CoA. And in the next video, I will talk to you guys about beta oxidation. Beta oxidation, these are the steps that will break down the fatty acid into acetyl-CoA units, okay? This occurs in the matrix of the mitochondria. All right, so we'll do that in the next video.